In this video, we will be looking at designing shell and tube heat exchangers, the different methods of calculation, the idea of degrees of freedom as applied to heat exchanger specifications. For this video, we will be using a component list as shown here. This is the Peng-Robinson package, the fluid package we'll be using. The component list is shown here. No reactions are used in this video. We will set up 4 streams. 2 of the streams have information provided and are fully defined. 2 of the streams have no information provided whatsoever. These are the conditions for the boiler feed water stream and the composition. This is the composition and conditions for the hot gas stream, which will be used to make steam from the boiler feed water. As said earlier, no information is provided for these 2 streams. We will now add a heat exchanger unit up to the flow sheet. You can exchange the icon and choose an icon that best suits your needs. So, in this case, the boiler feed water will be fed to the shell side. The hot gas will be on the tube side. So the tube side inlet will be the hot gas. The tube side outlet we will specify as cool gas. Boiler feed water, saturated steam. Note, for either side of the exchanger, you can specify the fluid package that is applicable. This is useful for when there are systems that may be using components that are compatible with one fluid package on the tube side and another fluid package on the shell side. An example of this may be using glycol as a coolant for hot oil. The oil may be used on the tube side and may use the Peng-Robinson package, and the glycol would obviously use the glycol package on this side. One parameter that must be specified is the delta P. With respect to shell and tube heat exchangers, a typical delta P would be around 5 psi. This of course varies with the exchanger design, the number of tubes, the tube diameter, the velocity through the tubes, etc., degree of fouling. Next, we go to the specifications page. Here we can see that the degrees of freedom is 1, meaning that we need to specify one further piece of information in order for the exchanger to solve. The UA can be specified. In this case, an active spec is a spec that is used towards the calculation. In this case, even though the spec is active, it is not used towards the calculation because the degrees of freedom is still 1 and it is empty, you can deactivate a spec by checking the box or removing the check from the box. We will now add a specification. We will add a specification such that we will place a temperature on the outlet stream, and the stream in question would be the cool gas. Here we will drop the cool gas temperature to 260 degrees Celsius. Note we get a message that the FT correction factor is low. You can choose to ignore that message, as this is a simple heat balance type calculation and a formal design for the exchangers, including its geometry, is not considered. Note, however, even though the FT factor has been ignored, there is a temperature cross. The hot gas comes in at 345 degrees. The boiler feed water at 30. The hot gas, as we specified, exits as 260, but note the saturated steam is exiting at 1672. This is higher than the hot gas, and therefore it is physically impossible for the hot gas to actually heat the steam up to this temperature. So specifications not only need to match up in terms of the degrees of freedom, but they must also be physically viable. We will take off this specification. In fact, we may delete the specification as we think about a specification that is more applicable or one that can be realized. Note the degree of freedom is 1. A specification that makes more sense is to specify that all the water entering the exchanger is vaporized. By specifying a vapor fraction of 1, we are saying that all the water is vaporized and is at its saturated conditions. Note the temperature is now 299.9 degrees, which is determined from the phase relationship. The pressure is determined from the pressure drop we specified in the exchanger. Now the exchanger is running what we call a simple endpoint model, and this model is based on an energy balance around the exchanger to determine the temperatures. It does not take into account the geometry of the exchanger. We will now reactivate the FT correction factor, which tells us that there is an exchanger that is possible that can do the service. To find this exchanger, we will use the auto size, rigorous shell and tube. We may also use the interactive sizing for the rigorous shell and tube. The difference between the two is the interactive allows us to set some of the variables that will be iterated upon. So, if you need to maintain an exchanger tube diameter of 1 inch or an overall tube length of 8 inches, choosing interactive allows you to set that and allow the other parameters to be calculated. We will use the auto size. This may take a little while. What the auto size utility does is that it runs multiple iterations similar to the Kern's method to determine which physical geometry will actually work to give us the desired heat transfer coefficient and surface area. I will pause the video while this operation takes place. Here we can see the evaluation taking place. Multiple designs are being tried in an iterative method, as I said, similar to the Kearns method. Designs have been found that are near. Soon we will find designs that are okay. Multiple designs that are okay will be evaluated to determine which is the most financially feasible design. These designs may have UA values that are higher than the UA value desired, and as such, the designs will be modified slightly by changing tube length or by changing tube diameter to determine which combination is best suited to the service. Right. A design has been found and applied, and you would notice that the heat exchanger model has changed to rigorous shell and tube. However, we have a yellow bar. That yellow bar is telling us that there is a reason that we don't have a solution. One would remember that we specified a value for the vapor fraction of the saturated steam. Now that a full rigorous model of the shell and tube heat exchanger has been established, we no longer need to specify any outlet conditions. That is because we have the geometry to calculate the UA value from the film coefficients. Hence, if we delete the specification, we will see that the model will solve. This model is now representative of a real heat exchanger in service, and as such we need not specify any outlet conditions. Let's take a deeper look at the rigorous model. You will notice now that under the rating sheet we will be able to find the information loaded for the rigorous model. The number of shells in series being 1, number of shells in series being parallel being 1, and 2 tube passes per shell, the first tube pass being counter current. By clicking on the shell icon, we can see the shell diameter in millimeters. Hover over it, we can get it in inches. You can get the tube pitch and the number of tubes per shell. You can get information about the baffles and of course information on the tubes, such as the tube outer diameter, inner diameter, thermal conductivity, and so on. We can also take a deeper look at the performance of the exchanger. Plots for the exchanger. Very difficult to see at this point. For the tube side and the shell side. We can get the UA value and the LMTD. We can look at the exchanger in more detail by clicking on the Model Details button on the Rigorous Shell and Tube exchanger. This will bring up a window where we can get information about the exchanger that you would not normally find within HYSYS. You can see a drawing of the exchanger. You can see the temperature profile of the exchanger. You can see the tube layout. You can look at the results summary. Any warnings or messages that may have come up. Here they are saying that we specified 2-phase properties, but only a single phase was detected. We can even get a teamer sheet for the exchanger. Note, if you have an exchanger in service already, it will have a design and a teamer sheet. You can create that exchanger or a model of that exchanger in HYSYS by specifying the rigorous shell and tube model and then entering the information on the model under the rating tab. Under the sizing sheet, you can fill in the information for the tubes, the shell, and overall. Now, a rigorous model is a much better model than a simple endpoint model. The reason for this, it is sensitive to changes in input flows. For example, if I were to drop the inlet temperature of the cool gas to 330 degrees Celsius, the model will now recalculate what the outlet conditions are for both the saturated seam side and for the cool gas. As we expect, with less energy coming in on the gas side, we should no longer be making saturated steam with all of the water. And here we can see that a fraction of the steam is vaporized, much less than before. This brings an end to the shell and tube heat exchanger model video.